Hello and welcome to my first basic engineering video where I will be going over some basic engineering principles. Today, obviously, if you've clicked on the title of this video, I'm going to be going over nonlinear and linear regression. And I'm going to be getting into why it's so important for engineers to understand the difference between linear and nonlinear regression. So as you can see here, I'm going to be explaining linear and nonlinear regression using vapor pressure models as well as Antoine's equation. So what is Antoine's equation? Well, Antoine's equation explains the relationship between pressure and temperature. And it looks like this. Log base 10 of P is equal to A minus B over C plus T. That's Antoine's equation. So, like I said, it's the relationship between pressure and temperature of a specific substance. So, P being the vapor pressure, and T being the temperature. So you might be asking, what is A, B, and C? Well, A, B, and C are the coefficients of that specific liquid that we are relating between pressure and temperature. So these are going to be the important numbers that we're going to be looking for so we can understand how pressure and temperature vary together. So A, B, and C are the coefficients. So I'm going to keep this up here because it's important and we're going to have to use it throughout the video. So let's get started. First of all, obviously, we're going to need some sort of data. And I don't have a Bunsen burner with me here in the library, so I'm going to have to use some data that has already been collected. So here we can see we have these data points of temperature and pressure. And we have about quite a few of them. So I'm going to take this as raw data so we can use it. And here, again, this is the exact same thing. It's just pressure and temperature that have been recorded. So I'm going to take this website that's been saved as raw data. I'm going to copy it. And then I'm going to open up a Google Collaboratory. So here we are in Google Colab. It's just Python code, and it's a lot more user-friendly. So I'm going to want to get that data that I just found, or that I took, excuse me. So I'm going to take it from a website, and then that is, again, the same website that we just took the raw data from, this that we just copied. I just pasted it in there, and I'm going to hit Shift-Enter. It's going to load, and we have success. So it says that water vapor pressure.csv has been saved, all 1,300 points of it, and it's saving to water vapor pressure.csv. So this is important. That's what has been saved as my collab. So I'm going to copy this. And then the next thing we're going to need to do is we're going to need to use some numerical data. Obviously, we're going to be using numbers. So we need to import numerical Python into my collab. So import numpy, that's numerical Python, as np. There we go, success. So we have our data, or we've inputted that that data as a website, and we've imported numerical Python. So the next thing we're going to want to see is we want that data as a variable. So data, we're just going to call it data, is numerical Python, and remember we saved this as text. So we're going to say dot load text, and it's popping up with different options as I type, which is very helpful. Dot load text, and then what kind of text are we going to want to load? Well, because Colab is so helpful, it already told me what it's saved as. So saving to water vapor pressure.csv. That is the name of the file. So I'm going to copy that and paste that in. Perfect. But also remember, this raw data isn't just one column of numbers. It's two columns. It's our temperature and our pressure, which I don't believe I said. This is also very important. Our temperature is in Kelvin and our pressure is in pascals. That's going to be important later as well. So, excuse me, I'm sorry I forgot to mention that, but I'll keep that up there as well because we'll need to know that. So, this is our raw data in Kelvin and pascals, and it's not just one column, it's two columns. So to differentiate that, we are going to say that the delimiter is equal to a comma. So that's how we can tell Google Colab to differentiate between the two different columns. So shift enter, and then that works. So let's take a look at it. We want to make sure that that worked. Data, shift enter. And there we go. It's been saved as an array called data. And then this, as we can see, is the same as the raw data that we just took. And now it's in our Colab. So what do we want to do next? Well, we saved the array. We know that it's our temperature and our pressure, but so far our Colab file doesn't know that it's temperature and pressure. So let's assign some variables to the first column and the second column. So the first column is our temperature in kelvins. So I'm going to call it temp. And it's going to be equal to our data array. And it's going to be the first column. So every row, column 0. But you might be asking, why are you saying column 0? Well, Python numerically starts at 0 and then works its way up. So the 0 column would be technically the first column, the 1 column would technically be the second column, and so on. So temp equals data, all rows, column 0, shift enter. So let's check and make sure that that makes sense. Perfect. Now it's saying that our variable temp is our first row of data for our temperature in Kelvin. So now I want our pressure. But let's think. Let's go back to our board. And we see that for Antoine's equation, pressure isn't just pressure. It's log 10 of pressure. So Antoine's equation isn't pressure equal to A minus B over C plus T. It's log 10 of pressure equal to A minus B over C plus T. So because I don't want to forget that, and I want to make sure that we are sticking to our Antoine equation, I'm going to call this variable log pressure is equal to data of our second column. Oops, excuse me. But remember, it's our second column, but we're calling it our first column because technically our first column is our 0 column. But you might be asking, if this is log 10 of pressure, don't we need to make our data log 10 of pressure? And you'd be completely correct. So I'm going to be taking from numerical Python log 10 of our data. So now instead of just having our pressure, we're going to be having log 10 of our pressure. And it worked. So let's check and make sure that it worked. Perfect. It came up. So now we have our data saved as an array of 2 columns that we took from raw data. We imported as text. And now we've assigned variables to our temperature and our log pressure. So what's next? Well, I'm a very visual learner. So let's turn this into a graph. Let's turn it into a scatter plot. So just like we had to do with numerical Python, we also need to import a way of plotting something. And I'm going to be using plotly.io. So from plotly.subplots, I'm going to be importing and I want to make subplots. Also, please bear with me if I make mistakes. I'm always going to make mistakes. That's part of being an engineer. So, but the important part of making mistakes as an engineer is that I work through them. So, import plotly.subplots, import make subplots. That looks correct. And then I'm going to be import plotly.io as io. Okay, if I did it correct, I now should have plotly. So I have my data. I have it saved as temp, and I have the temperature saved as temp, and I have the pressure saved as log pressure. So I'm going to want to plot it. So I'm going to make a figure, and then just like I said up here, I imported make subplots, so I'm going to make subplot. Okay, let's see. So my rows and columns, I have rows equal 1, columns equal 1, and that makes sense. Name make subplots. It says make subplots is not defined. Oh, there we go. I forgot the S. My mistake. So next I'm going to do fig.add. I'm going to, I want to add a scatter plot. So add scatter. And then I want my x variable to be the temperature. And I want my y variable to be the pressure temperature that I created. And then because I'm making it as a scatter plot, I don't want it to be a line. I want it to be dots. So I'm going to be making the mode as markers. And then I'm going to give it a name. Because this is just my regular data that I just want to see what the data looks like on its own, I'm just going to call this the original data, so OG data. And there we go. It worked. So here I have all my different points at different temperatures at certain pressures. So up next, I'm going to be showing you, so let's do a recap. So I was able to get my raw data. I imported it in as text. I imported numerical Python and Plotly so that I could make different plots and graphs. I saved the data as an array, and then I assigned values to the two different columns in my array. So my temperature in Kelvin and my pressure, in pascals. So as temp and log press, I made a figure so I could see my data, and it came up with this nice little plot. So next, I'm going to be going into nonlinear regression. So far, all we've done is plot our raw data that we found offline, that we created in the lab, and then we imported it into Python. So our next step is going to be just understanding nonlinear regression. So here we have on the board, remember, our pressure is vapor pressure, our P is vapor pressure, our T is temperature, both in pascals and Kelvin, and then A, B, and C are coefficients. So right now, we have our scatter plot of a number of different points. And this is nonlinear regression that I'm discussing right now. So we have our points, and make these a bit bigger so you can see them. Do you see them all right? Okay, yeah. So this is our scatter plot. And then in order to do nonlinear regression, obviously we need a line. So we have a line going through our graph. And then How does this make it nonlinear? Well, we're going to be adjusting this line to best fit our data points. And we're going to be doing that with something called the sum squared error. Or SSE. So what exactly is the sum squared error? Well, as an equation, the sum squared error is the sum, starting with I equals 1 up to n, of our pressure initial minus our Antoine's equation. So A minus B over C plus T. So, oh, I made a mistake already. This isn't pi, it's log pi. There we go. So that's our sum squared error. But what is an SSE? What is a sum squared error? Well, if you take a look at our data points, our line doesn't hit every single data point. In fact, there's certain distances of gaps between each line. So these gaps show the difference between the plotted model of our line and the actual data points. And you can notice some of them are different lengths. This one obviously is a lot smaller than that one. So these are our errors, and the sum of them make up the sum squared error. So by adding up all these errors together, we can help indicate the changes that we need to make so that our plot best represents our data. So how do we do that? Well, like I said earlier, the key is going to be in these coefficients. So we have our pressures, our initial pressure all the way up to n for all the data points that we made. We have our temperatures that we reach based on the pressure. So the only things we can change are these three variables from Antoine's equation, A, B, and C. So by changing these coefficients or these variables of A, B, and C, we can find a plot, a line, that best fits this data and minimizes the error between our plotted line and our data points. So that's the key. We want to minimize our sum squared error. And by doing that, we can create a plotted line that has the least amount of error, or the least amount of distance between these lines. So obviously that's not going to make a straight line. It's going to make a curved line depending on the data points. This is just an example. This isn't accurate to the data that I'm using. But that is why it's a nonlinear regression. And that's why we want to minimize our sum squared error, so we can plot something as accurately as possible to our data points. But you might notice, hey, we have some data points that are underneath the line and some data points that are on top of the line. So if we're trying to measure the distance between our line and our data points, this error might be positive, or this error might be positive, and then this error might be negative. And you'd be right. This is a positive error between our line and our data point, and this is a negative error between our line and our data point. So technically, if we're going to sum all these up, we're going to have positives and negatives all across the board. It's going to make it really nasty and difficult to work with. So, in order to do that, one way we know as engineers to get rid of negative signs is just to square everything. So that's exactly what we're going to do. We're going to take our sum squared error, we're going to put it all in parentheses, and we're going to square it. So now we understand what the sum squared error is. We understand why it's important to minimize it so we can have a more accurate nonlinear regression. And we're going to square our sum equation so that we can get rid of all of our negative values. Now that I've explained the sum of squared errors and why it's important to minimize it to make our nonlinear regression fit best to our data points, now I need to get the sum of squared errors and the minimization of the sum of squared errors into our Google Colab. So here's how we're going to do it. First, we need to define what our sum of squared errors is so that Python can understand it. So we're going to be defining it as v for a vector. And the reason why it's a vector is because our a, our b, and our c variables, which are the coefficients that we're trying to change and optimize to minimize the error between our data points, those are the actual things in the equation we're going to be changing. So here we have a, b, and c as our vectors, and we need to do return. Now we're going to input our equation. So our sum of squared errors equation is going to start off with a sum. So that's from numerical Python, so np sum. And I have to be very, very careful with my parentheses here because this equation can get long. So log press, we're still using our pressure variable that we made all the way up here, log press. Yes, log press minus, and we can always go back and check our equation. Log press minus a minus b over c plus t. So minus a minus b over c plus temp. Remember, our temperature variable is still the same. So, and then remember, just like what we said, we need to square all of this, including the log of the pressures and our Antoine equation, in order to remove those negative values. So to square, we do star star 2, and there we go. So far that makes sense. So we've defined our sum of squared errors, we've inputted our sum equation, and now we need to do a minimization. So just like we had to do with our numerical Python, and just like we had to do with our plotting Python, we need to import a minimization from somewhere. So I'm going to be doing from Science Python, SciPy, and it's going to be optimization, scipy.optimize. I'm going to be importing the minimization input. So import minimize. Make sure that works. Looks like it's all good. So now that we have minimize, we can minimize our sum squared error so we can get the best nonlinear regression. So minimize our sum squared error, and then in order to minimize it, Python can't minimize it unless it has somewhere to start. So we're going to be giving it some starting points for a, b, and c, our vectors of the SSE, of the sum squared errors. So I'm just going to do 10, 10, and 10. There we go. So what did we get? Minimize SSE array. Okay. Optimization terminated successfully. So hopefully this works. I'm going to keep going, and if it comes up with an error, we'll have to go back. So, but we're minimizing our regression based on our vectors a, b, and c, our vector a, b, and c, which are our determining variables. So I want to give them a new title as variables because this is a nonlinear regression. So a and l are a for our nonlinear regression, b and l are b for our nonlinear regression, and c and l are c for our nonlinear regression. Minimize, and then the same thing, sum squared error, and then our guess, 10, 10, 10, which are our guess for our initial variables for A, B, and C. Too many values to unpack. Okay, let's go back to this because it's most likely an issue in here. A minus B over C plus temp. Most recent call last. Oh, I see. Okay, we need to do point X. There we go. So that shows that we are just looking for A, B, and C through our X column because it's only in relationship to temperature. Doesn't affect our pressure, it's with temperature. So dot X. So now let's see what the nonlinear regression looks like with a scatter plot. So again, here we added a scatter plot using markers to see our data points. Now we're going to add a scatter plot to see our nonlinear regression using lines. So fig.add scatter. Our X variable is still going to be the same. It's still going to be temperature. And our Y variable is now going to be our equation using our new nonlinear variables that we just made. So A and L, B and L, C and L. So A and L minus B and L over still temp, so it's still our temperature that we made up here, temp plus C nonlinear. And then be careful with our parentheses. So there we go. I'm going to add one in here just for good measure. And then our mode, like I said, is not going to be markers. It's going to be lines. And then I'm going to name this as non-linear. Invalid syntax. Oop, I must have messed up. Oh, too many parentheses. Okay. So I'm having some issues. Here we go. So here's our nonlinear line represented with our original data. So if we can zoom in maybe, oh here we go, zoom, we can see that our data is being fit using a nonlinear regression line. So next we'll be going into linear regression, which is a little bit different from nonlinear. So to recap so far, all we have done is take raw data of temperature and pressure and turn it into nonlinear regression using our Python Colab. Now I'm going to go into linear regression, which is a little bit different but also just as important to understand. So just like we began with our nonlinear regression, we're going to start off with Antoine's equation, which if you remember is log of our pressure is equal to A minus B over C plus temperature. So in order to do this linearly, we're going to turn it into matrices. The first step of adjusting this equation, I'm going to multiply out the C plus T. So I will get C plus T times log P is equal to C plus T times A, minus B. So all I've done is taken this numerator or denominator of C plus T and multiply it out. The next step I'm going to do is simplify this a little bit further. So I'm going to take t log of p is equal to ta minus c log of p plus ac minus b, which I'm going to put in parentheses. C plus t. Okay, that makes sense. So, t log of p is equal to ta minus c log of p plus ac minus b. As you notice, ac minus b is made up of all variables. So I can simplify this by turning this into a new variable, which, to keep everything simple, key is simplicity, is to turn this into d. So now I can write it out as t log of p is equal to ta minus c log of p plus d. You can notice that out of all the variables that I began with, a, b, and c, now I have a, c, and d. I factored out d because it is part of the new variable d. So what's the next step? The next step is to turn everything into matrices. So we're going to need a design matrix. I'm going to start off over here. You can see temperature, log pressure, and then the variables. So start out with temperature, log pressure. I'm going to stop right there, and I need to turn this into a matrix. So T1 log P1, T2 log P2, T3 log P3, all the way to as many data sets as we have. I don't remember the number, so it's Tn log Pn. And we're going to multiply this by, what are we going to multiply it by? Well, our variables, a, c, and d. So we're going to have another one, which is just one column, a, c, d. But you notice this is a 3 by 2 matrix, and this is a 3 by 1 matrix. And you can't multiply a 3 by 2 matrix and a 3 by 1 matrix. So what I'm going to do is I'm going to add in another column for our first matrix of just a bunch of ones, which now turns this into a 3 by 3 matrix. And I can do that because if you multiply anything by 1, it's going to be the same for what it is. So this is our design matrix. And I'm just going to call it big X. This is our vector, so I'm going to call it V. And then we're multiplying these two matrices together to get something. So we're going to get, if we do a 3 by 3 times a 3 by 1, we should get a 3 by 1. It's basic matrix multiplication. So get T1 log P1, T2 log P2, T3 log P3, all the way to some Tn log Pn. And this right here should be our final matrix. So this times this equals this, which makes sense because we have T log P, TA C log P. So it matches our equation. Okay, I'm going to make some room. And switch over to this side. So I'm going to call this big Y. So we have X times V equals Y. These are our matrices. And to get this into linear, I'm going to use a transpose. I'm going to take x transpose x times v is equal to x transpose y. So remember, this is still our 3 by 3. This is still our 3 by 1. This is still our 3 by 3. I've just multiplied our x and y by transpose. Now, I'm going to multiply it by an inverse so that we can get our identity matrix. So, what is that going to look like? There we go. So here, our x transpose, oh, you can't see me. Here, our x transpose x to the -1 times x transpose of y, and our x transpose of x to the -1 times x transpose of x. This is our identity matrix. So, how are we going to work with this? Well, let's jump back into Google Colab. And so we are back in our Google Colab. We just went through all the linear algebra it takes to format our regression as linear. And now all we have to do is start inputting our design matrix, our inverse matrix, and our vectors, and start putting them in to Python. So first off, I'm going to start with our big X design matrix. X is equal to, and we're going to be using numerical Python again for C of, it's going to be temperature, log pressure, and then ones. So temp, and then minus log press. It is minus. That's my mistake. These should all be negative. If you can see these. Negative, 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 negative. My mistake. Yeah. Negative log press. And then we need to add in a column of ones that is the same length as the log and the temperatures. So how do we do that? Well, we use numerical Python. So np ones like temp. So what I'm saying here is that add in a numerical column of ones that are the same length as the temperature column. Okay, seemed to work. So let's test it out. Show us what x looks like. Perfect. So we have a 3 by 3 matrix of our temperatures, our negative log pressures, and then a column of ones that is the same length. So that's our design matrix. Next, we're going to do the transpose times our design matrix. So x.t at x, and at is the Python equivalent of for matrix multiplication. So I'm going to do that, and we get a 3 by 3, which is what we want. Now, we need to do the inverse. So numerical Python, we use linear algebra, linalg, inverse, inv, of our x transpose times x. So now we have our inverse of our transpose. And to take it one step further, we do the same thing, linalg dot inverse of our x transpose at x at x transpose at our temperature times our pressure. So temp times, this is just a star, it's not an at because these aren't matrices, these are just columns. These are just data points, excuse me. Temp at log press. And it gives us a 3 by 1. So, or a 1 by 3. So, yep, okay. So, next step is now we've taken the inverse using linear algebra and numerical Python. We need to assign these 3 numbers to our 3 variables that we decided on. So, A, C, and D. And remember, D is just a more complicated variable that we've turned into a single letter, but it uses B. So, just like we did, if I go back up to our nonlinear, we used A and L, B and L, and C and L. Now we will be using A, C, and D. So A, L, C, L, D, L is equal to this 10, negative 34, and negative 2, 1, 2, 3. So if I copy this, put it here, Shift Enter. So now we've assigned these 3 variables to these 3 numbers. So A, C, L, D, L. So what's left? Now we just need to plot it so we can see the linear regression. So I'm very lazy, and I'm just going to copy the code that we already wrote for our nonlinear regression because it should be the same, but we just need to change a few important things. So it's still figure, add, scatter plot. X is still temperature. Our Y is going to be different. We'll get to that. The mode is still lines. We still want to see it as lines. And this is going to be nonlinear. It's going to be linear. So our Y is going to be Antoine's equation. So A underscore L minus B underscore L over temp plus C underscore L. Mode lines, name linear. And there we go. So if you notice, now we have done it linearly, non-linearly, and we have the OG original data. So if we go back up, here is our original data, plotted out as just data points. Here we have it as nonlinear regression through those data points, and now we have it as linear regression through those data points. Well, you must be asking, they look essentially the same. That's true, but if you zoom in again, get a little bit closer. Oh, now I can see the linear and the nonlinear. Zoom in again. Look at that. They're different. Not very different, but they are different. But when you look at it from the auto-scaled version, you can barely tell that they're different. So, we've covered a lot of main points in this video. Linear regression, nonlinear regression, sum squared errors, the linear algebra with the matrix multiplication to get to a linear regression, and basic matrix multiplication. I hope you found this video helpful. I know creating it was very helpful to me, and I look forward to creating more videos in the future.